In this project, we introduce P2GS, physical prior-guided Gaussian splatting for photometrically consistent urban reconstruction. 3D Gaussian splatting provides high reconstruction quality and fast rendering. It is also highly editable, making it suitable for simulation tasks. However, it is sensitive to real-world noise, such as motion blur and calibration errors. A key challenge is illumination inconsistency across cameras. Brightness varies from view to view due to various factors, such as differences in exposure, auto-white balance, and light sources. These inconsistencies are baked into the Gaussians and degrade reconstruction. There are two approaches for brightness adjustment. One is hardware-based, such as exposure settings. The other is software-based, such as tone mapping. Gamma correction is especially important, as it applies a nonlinear transformation to linear luminance. However, tone mapping is nonlinear and distorts physical radiance. This makes it difficult to accumulate light consistently. Conventional methods predict HDR and tone mapping with neural network, but they lack physical constraints. Our goal is to estimate true HDR radiance and camera setting. We solve the inverse problem from LDR images to recover radiance, exposure, and tone mapping. However, the solution to this problem is not unique. So we introduce physics-based regularization. Our model consists of HDR representation, view-wise rendering, and loss design. We explicitly separate radiance and camera parameters. We represent the scene using linear HDR radiance and render it via volume rendering. Then we apply exposure and tone mapping to obtain LDR images. Exposure is modeled as a scaling factor. Tone mapping is represented using a gamma function. This is simple but physically interpretable. We optimize the model in an unsupervised HDR radiance. The loss consists of photometric loss, exposure consistency loss, and regularization. The photometric loss is the same as in standard 3D-GS. The key component is the exposure consistency loss. It is based on the principle of invariant radiance. Radiance should be identical across cameras, up to exposure differences. We also regularize exposure and gamma to stabilize training. We evaluate our method on the Waymo open dataset. Compared to baselines, our method improves most metrics. Especially, it achieves better perceptual quality and consistency. Qualitatively, our method removes illumination differences between cameras. It produces more natural and consistent reconstructions. In other method reproduce GT and express the illumination difference. But our method can remove illumination differences between cameras. In the Waymo dataset, the ground truth itself contains illumination differences, which makes accurate evaluation difficult. To address this, we construct a dataset using Carla. This slide shows results on static scenes. Our method significantly improves all metrics compared to other methods. Importantly, performance degradation under larger exposure variation, such as standard 4, is minimal. This slide shows results on comparison with dynamic scene models. StreetGS and OmniRe show smaller delta PSNR than ours, but suffer large drops in other metrics. In baseline methods, illumination differences are baked into the Gaussians. In contrast, our method removes these inconsistencies. Our method not only delivers excellent reconstruction quality, but also allows for the use of arbitrary parameters during rendering. In this example, we are varying the gamma value. You can also adjust the exposure scale or choose whether to apply tone mapping. Our method allows you to change camera settings without slowing down rendering. In conclusion, we propose P2GS to achieve photometrically consistent reconstruction. We separate radiance from exposure and tone mapping and improve robustness and quality. Thank you for your attention.